Good morning, Knights. Welcome back to Chemistry Online. Today we're going to be working on the exam review that I gave you guys last class. I'm not going to work through the entire review. I'm going to work through about half of it just to help you guys get the ball rolling. Once we're finished with the first half, you're going to be expected to finish the second half on your own. The second half is more recent stuff. We've been working on it over the past 4 or 5 weeks. So I expect that you'll have better memory of that stuff. After Friday, you're going to be receiving a late grade for this. So be sure to turn this in by tomorrow. And the exam is going to be next week. It's not going to be a very long exam. It's actually going to be about half of this. So probably 20 to 25 questions covering every piece of material that we go over on this exam. And yeah, I have no concern. I'm pretty sure you guys are going to do very well on that. The way I'm recording today is a little bit different than usual, so I hope you guys don't notice too big of a difference, but just know that that's why I'm going to be making a few mistakes as we go through this. Alright, so question number 1 says, the air is a combination of several different gases including oxygen, nitrogen, and carbon dioxide. Each gas has a different set of properties. That means the air is what? Is air a pure substance or a mixture? So to be a pure substance, it could either be a compound or it could be an element. We know that air is neither an element or a compound because it has O2 in it, it has N2 in it, it has CO2, it's got CO, it's got all types of things in it. So therefore it's a mixture, not a pure substance. So the answer to 1 is no, not that. Yeah, I don't know how to undo, so B is what we're going to put for number 1. Number 2 says, one way that mixtures differ from pure substances is the method that we can separate them into their components. Which of the following is a method used to separate components of some mixtures? So here we're looking for a separation method. A nuclear reaction is not a separation method. A filtration process, that one actually is a separation method. Yeah, the annotation is not good. I can't even get a check mark. So a chemical reaction, is that a separation method? So chemical reactions can be a separation method, but that's not really what we're looking for here. And then electrolysis, that's also kind of a separation method, but it's not for physical yeah, so these 3 are meant to confuse you, or these 2 really are meant to confuse you. A chemical reaction, that is a way that we could separate some things, but it's not really a separation method. And electrolysis is also a way of separating things, but it's not a separation method. The only separation method we have here is filtration. And if y'all remember, there was filtration, there was sieving, there was there's a few other ones, decanting, and we'll get to them as we move forward. Number 3 says, which class of matter can usually be physically separated by hand? All right, so can you separate compounds by hand? Can you separate H2O into hydrogen and oxygen by hand? No, you can't. That's really what electrolysis is for. But you cannot separate compounds by hand. Can you separate elements by hand? Well, you can, like if you had a large thing of, I don't know, gold, just pure gold, and you wanted to separate it, you could separate it by hand. We'll leave that one as it is. Well, I guess it depends on how you define separate. Like I guess they don't mean break apart, because if you break something in half, you are separating it, but you're not separating it in the sense that they're asking. So we'll just go ahead and cross out element. Then we have heterogeneous and homogeneous mixture. So can we separate a heterogeneous mixture? Think of that like a bowl of Lucky Charms with no milk. So you have the marshmallows, you have the cereal part, and you could separate that by hand. So a heterogeneous mixture, we can separate it by hand. Another example would be like a fruit salad. You can separate the grapes from the strawberries, from the cucumbers. Well, you don't put cucumbers in a fruit salad, but you can if you want. Nobody's stopping you. Next, we have a homogeneous mixture. An example of that is going to be perfectly stirred chocolate milk. Can you separate the chocolate from the milk? So you could wait, maybe eventually some of the chocolate's going to fall, but can you separate the chocolate from the milk? Not by hand. So the correct answer to this one is a heterogeneous mixture. This is a question you're very likely going to see on the test, exactly how it's written right now. So you need to know that heterogeneous mixtures can be separated, while homogeneous mixtures cannot be separated by hand. All right, so the next one. Which of the following examples is evidence of a physical change? So we're not looking for a chemical change here. We're looking for a physical change. And one thing to know about physical changes is that typically they're easily reversible. So they can be reversed. All right, so first one is going to be a bowl of ice cream melts, ice cream melts in a bowl. So this one actually might be a physical change. Because if you take that ice cream, put it back in the freezer, it's just going to freeze again. So that is a physical change. Let's take a look at the next one. A silver spoon tarnishes over time. So that is not a physical change. That one is a chemical change. Basically, tarnishing silver is the same as rusting iron, but it's a chemical process. Next one says an electrical current splits water into hydrogen and oxygen. That's the definition for electrolysis, and that is not a physical change. That's a chemical change. A person inhales oxygen and exhales carbon dioxide. That's a chemical change that's going on inside your body. So that is not a physical change. That's chemical. So ice cream melting in a bowl is the only answer that works here. All right, which of the following is not a chemical property? All right, so whether or not something is flammable or not, is that chemical or physical? That's going to be chemical. Reactivity, so whether something reacts with something else or not, that's also going to be a chemical property. Toxicity, whether it's toxic or not, that's also going to be a chemical property. The only physical one we have here is going to be density. You're just going to have to remember that. Density is a physical property, not a chemical property. And you're very likely going to be tested on this too. All right, which of the following represents a chemical change? So here we're looking for something that's not physical, not easily reversible. A chemical change, so iron rusting underwater. So rusting, that is chemical change, and rusting is a keyword here. Let's look at the other ones though. So copper solid breaking into small pieces. So breaking, that's a physical change, not a chemical change. Solid iodine subliming. So a lot of people will pick C for number 6. C would be incorrect. So when something sublimes, that's a physical change. Just look back in your journal, look at the phase changes, the 6 phase changes, and sublimation is a type of phase change, and all phase changes are physical. Water melting under high temperatures. So melting, that's another phase change. So all 3 of these are physical. This is the only chemical we have here. All right, which of the following correctly describes the particles in a solid compared to the particles in a liquid? So here you need to read all of these to choose the one that works best. So particles in a solid are farther apart than particles in a liquid. That's not true. So solids, they're the ones that have the molecules that are closest together, because they're, think of ice. All right, so particles in a solid are farther apart than in a liquid. That's untrue. Next one says particles in a liquid are much farther apart than particles in a solid. So this one could be true, but we're going to need to read the rest of them. So particles in a solid do not move at all. So we know that that's not true. So we can go ahead and X that out. So particles in a solid, they vibrate in place, which is a type of movement. Particles in a solid vibrate in place, and particles in a liquid slide past one another. So there's nothing false about this statement. So we're just going to go with D. D is a lot better than B, because here to say much farther apart, they're not that much farther apart. They're slightly farther apart, but D is a perfect explanation. So we're going to go with that one. Which state of matter is most compressible? Y'all should easily remember this. So compressible means able to fit in a smaller container. And solids could never fit in a smaller container. Liquids, they also can't really fit in a smaller container. They're slightly compressible, whereas gases could easily be fit in a smaller container. So gases are going to be the most compressible. Solids and liquids are not. Which state of matter has definite volume, definite shape? So definite volume, We know that's not a gas. Definite shape, we know that's not a liquid, so that leaves us with a solid. And I know plasma's included here, but I already told you guys plasma's not going to be the answer to any of these questions. So don't worry about plasma. I would ignore that. It's just a freebie. Which state of matter has definite volume and no definite shape? So definite volume but no definite shape, that's going to be our liquid. You're probably going to see one of these, so be ready for it. When a sample of gas is cooled, it condenses into a liquid. In which of the following ways does the molecule of the original gas sample compare to the molecules of the liquid? All right, so when a sample of gas is cooled, it condenses into a liquid. In which of the following ways do the molecules of the original gas compare to the molecules of the liquid? All right, so they're asking us here to compare gas molecules to liquid molecules. The molecules are larger as a gas than they are as a liquid. That makes no sense. Molecules aren't going to get smaller or larger. The molecules weigh less. That's also untrue. The molecules move faster as a gas than they do as a liquid. That one's perfectly true. Nothing false in that statement. But let's go ahead and read D. The molecules are closer together as a gas. That's a false statement. So C is the correct answer for 11. Which information provided by the periodic table can help identify an element's reactivity? That one's a very important question. You're very likely going to see this one again. So what on the periodic table tells you how reactive something is? Basically, it's placement on the periodic table, which row and which column it's in. But the answer to this particular question is going to be the column that it's in. And what do we call columns on the periodic table? That's not a period. That's going to be a group. The group number is what tells you how reactive something is. It's not the mass number, and it's not the atomic number. And I know atomic number is kind of in the ballpark, but it's not the correct answer. Correct answer is going to be group number. All right, number 13, which element contains 7 protons and 5 valence electrons? So, I don't have a periodic table in front of me. Let me open one up real quick. But I'm pretty sure it's boron. I don't want to tell y'all the wrong answer though, because y'all just gonna make fun of me. All right, so we're looking for an element that has 7 protons. So because it has 7 protons, we know that it's gonna have an atomic number of 7 at the top, and then 5 valence electrons. That doesn't really tell you what element it is, but 7 does. So on our periodic table, let me bring it over to this side. We're just gonna look for the one that has a 7, and that's gonna be nitrogen. I said boron. Actually, no. Yeah, boron's correct. No, nitrogen's correct. That's my bad. See, that's why we pull up a periodic table. So 1, 2, 3, 4, 5, 6, 7. 7 would put us right at nitrogen. Nitrogen's the correct answer for this one. I'll minimize this. We might need it later. So nitrogen is going to be the correct answer for 13. And this is why we always use a periodic table. So be sure to pull up your periodic table. All right, so 14 says, which statement can you use to identify an element? All right, so here are our answers. The element has 36 protons, so that actually is identifiable. And it just sucks when when answer A is correct, because then I shouldn't go through the rest, but I will go through the rest, just so we're all on the same page. So an element has 6 neutrons. So knowing the number of neutrons, it doesn't tell you which element you have, because neutrons are not equivalent to protons. Sometimes they are, but most of the time they're not. So neutrons do not tell you which element you're dealing with. The element has 8 valence electrons. Well, there's a column of elements that have 8 valence electrons. So that doesn't really help us identify which element exactly. The element has similar properties to nitrogen. That just means it's in the same group as nitrogen, but that doesn't tell you which element it's in, or which element it is. So the correct answer here is going to be A, 36. And if we look at our periodic table, 36, that's going to be krypton. Oh, bless me. Thank you. All right, so let's go ahead and look at 15. Which statement will most... excuse me. Which statement will be most helpful in determining an element's reactivity? So to figure out how reactive something is, the element has the same number of electron shells as iodine. This basically tells you which period it's in, and that's not the best statement at determining reactivity. The element has the same number of valence electrons as cesium. That actually does help us a lot. It tells us which group it's in, and knowing which group it's in tells us how reactive it is. The element has 47 neutrons. This doesn't tell us anything about the element, because there's multiple elements that have 47 valence electrons, 47 neutrons. You'd have to do the math, but just look at the periodic table, find a couple of them. It doesn't pinpoint which element you're dealing with. The element is metallic. That basically gives you more than half of the periodic table, which isn't helpful at all. The correct answer here is going to be B. All right, number 16 says that it has definite shape, definite volume. So we actually already saw this question. Definite shape and definite volume, that's going to be solid. Definite volume, but no definite shape. So as you can see, we have a couple questions repeated. These questions are very important. That's probably why they're repeated. That's probably why I put them in here twice. They're very important questions. So definite volume, but no definite shape. That's going to be our liquid. A combination of sugar and water is an example of what? So if you dissolve sugar in water, you're not going to see the sugar in the water anymore. They're going to become homogeneous. So homogeneous mixture. Another word for a homogeneous mixture is a solution. That's basically what number 18 is all about. The whole point of this question is to tell you that a homogeneous mixture and a solution are the same thing. And you're going to need to know that these words are used interchangeably. All right, 19. If matter is uniform throughout and cannot be separated into other substances by physical means, it must be what? So it's uniform throughout and it can't be separated through physical means. This one's actually a really tough question. I might have written this one myself, so it's got a lot of things wrong about this question. So if it's uniform throughout, then we know that it's a homogeneous mixture and it cannot be separated by physical means. It's a homogeneous mixture. That's the correct answer here. But, well, actually, yeah. So this was a very good question, because a compound and an element are neither of them are going to be a mixture. Well, actually, it doesn't say anywhere up there that it is a mixture. So don't worry about it. B is the correct answer for this one. It's a homogeneous mixture. But just to clarify, compounds and elements are both uniform throughout, and they both can't be separated by physical means. So this 19 is not a very well written question. You're not going to see a question like this on your ACP, which is the final exam. Which of the following is a physical change? So here we're looking for not a chemical change. Iron rusting underwater, we know that's a chemical change. Copper churning green in air, that's copper reacting with oxygen. So that is a reaction, which is a chemical change. Hydrogen and oxygen producing water, so that's a combination of two things creating something else. That's a chemical reaction. The only one here that's physical is going to be the one subliming. And the whole point of this question, and as you can see, this is the second question where subliming is the answer. The whole point of this is to let you know that sublimation is a physical change, not a chemical change. You're very likely going to see sublimation on the test. You're going to need to know that it's physical, not chemical. All right. So this section right here is worth 20 points on its own. This is not hard. You guys have done this before. But let's go ahead. I'm going to work through a few of them. I don't want to work through too many of them just because I could work through all of them, but who's got the time for that? Y'all aren't even going to watch this whole video. So I'm going to work through. I'll work all the way through. Let's work all the way to here. And the rest I'll let y'all do on your own. All right, so I'll pull my periodic table and put it on this side. So the first element we have is beryllium. Beryllium has an atomic number of 4, and if you're looking at your periodic table, you know exactly where that's at. And our atomic number and our number of protons and our number of electrons are always going to be the same. So this is going to be 4, this is going to be 4. If our mass number is 9, 9 minus our number of protons, that tells us our neutrons. So we have 5 neutrons. And it says complete symbols. So basically here it wants you to know how to do the nuclear notation. And I'm going to go over that real quick. I don't think I went over it very well when we talked about this before, just because of, you know, our setting. But there are multiple ways to write an element. The way that you're familiar with is the periodic table way, which gives you the symbol. So for beryllium, that's Be. And then it gives you your atomic number at the top. So you get a 4 here, and then you have a 9 down here. That's how the periodic table shows you them. What you need to know is that there's a nuclear notation. And let me show you that right quick. All right, so for nuclear notation, it's not that different. But basically, you're going to write out your symbol, so Be. And then your atomic number goes at the bottom, and then your atomic mass goes at the top. So this right here is the nuclear notation for beryllium. You need to know this. You will see it again on the test, and it might look confusing if we haven't really talked about it too much, but it's just something you should know. So this is regular notation, which is how it looks on the periodic table, and then this is nuclear notation. With nuclear notation, you write out the atomic number and the atomic mass previous to it, so to the left, and then atomic number goes at the top. So the larger numbers at the top, smaller numbers at the bottom. It's reversed, and I don't really know why we do it that way, but it is how we do it, and you need to know it. And these are basically the symbols that go in this box. But all I'm going to put is Be. So the next one, it gives us a mass number and it gives us a number of electrons. So we can bring this over here. And the one that has 8, that's going to be oxygen. So oxygen. And then number of neutrons is going to be 18 minus 8, which gives us 10. And our symbol for oxygen, I'm going to write out your nuclear symbol. But that's going to be O. And then at the top, we're going to have 18 and then 8 at the bottom. So that's our nuclear notation. Next one we have is aluminum. Aluminum is 13 for atomic number. 13 goes here too. And then our atomic mass is, it wants you to add these. So let's just add them together. That gives us 27. And then our symbol for aluminum is going to be 27 over 13 and then Al. All right, last one we're doing together. Neutrons are 32. Atomic number is 27. You add these together and you get 59. So our mass number is 59. And then 27, 27. And the element with 27, that one is going to be, that's cobalt. And if you could work through the rest of these, this is expected of you to turn in on the once you turn this in. And our symbol for cobalt is going to be CO. And then our nuclear notation is going to be CO58, or CO. That should be lowercase, so I'm just going to make this capital. CO5927. That's nuclear notation for cobalt. And that's all I'm going to work through here. Let's go ahead and move on to the last section. It says, in the chart below, identify if the example is a pure substance or a mixture, and identify if it's an element, a compound, homogeneous, or heterogeneous. This is super simple stuff. You need to know how to do this. So Kool-Aid, is it a mixture or a pure substance? So Kool-Aid is a mixture. We know that. You can't make Kool-Aid without mixing some stuff together. What kind of mixture is it? Is it heterogeneous or homogeneous? Well, once you've stirred it enough, it should all be uniform, and if it's uniform, then it's going to be homogeneous. Not an M, H. I don't think this is the correct spelling. We're missing an E here. All right, next one we have is iron. So iron, we know that's a pure substance. And iron is so to identify whether it's a element or a compound. So here it gives you it already gives you Fe. Fe is the chemical symbol for it on the periodic table. So if it's on the periodic table, then it's an element. If it's not on the periodic table, if it's a combination of things on the periodic table, then it's a compound. So iron is going to be an element. Pepperoni pizza. Let me draw one out for you. So you got the pizza and then you got the pepperonis on it. So if you look at this pepperoni pizza, it's not uniform throughout, but it is a mixture. So I'm going to put mixture here. And this one's going to be hetero. Last one we have is sodium hydroxide. And luckily it gives you the chemical symbol for them. So NaOH. And because you can see that it's a mixture of things on the periodic table, this one is going to be a compound. And you heard me just say mixture, but this is not a mixture. This is a pure substance. So compounds are considered pure substances. And the best way to think of that is water. Everyone knows water is H2O. I don't think anyone learned this in my class. This is just something that you know. Probably you saw that Arthur episode where they talk about H2O. But H2O is the chemical symbol for water. And you know that it's more than one element. It's two elements. And those two elements, they form water, which is a pure substance. And compounds are pure substances. That's basically what I'm trying to say here. And that's it. That's where I'm going to stop. I'll do 23. Actually, I'll do 23 and 24, and then that'll be where I stop. So for number 23, it says, given the representation of chlorine atom, which circle might represent bromine? So this one is a question that actually requires a little bit of thinking. So chlorine, it's asking us for chlorine and it's asking us for bromine. If you look at the periodic table, you can see that bromine is directly underneath chlorine. So because bromine is directly underneath chlorine, should it be bigger or smaller? It's going to be bigger. So we could already cross out B. We could cross out C because C is the same size. Correct answer for this one is going to be D. That one's a very simple one. You just need to, this is periodic trends. And we're talking about atomic radii here. All right, next one says which is the correct Lewis structure for fluorine? And y'all remember Lewis structures. They basically just show you how many valence electrons there are. And if you look at fluorine on the periodic table, it's group 17. Group 17 has 7 valence electrons. So the only answer that's remotely correct is C. And that's it. I'm going to stop right there. The rest of it's expected of you guys. I need y'all to turn it in Friday. So if y'all turn it in by Friday, then you could potentially get 100 on this. If you don't turn it in by Friday, there will be reduced points. Possibly an 80, possibly a 70. I'm not sure yet. But I just gave you half the answer. So you're already at a 50. I just want you to work the other half on your own.